Hello and welcome to our next lesson on factoring. This one is dealing with factoring quadratics where the a term is 1. We'll define what that a term is in a moment. Start with our curricular outcome. We'll take a look at quadratic structure and then how to factor these quadratics. Our outcome: students will be able to demonstrate an understanding of common factors and trinomial factoring concretely, pictorially, and symbolically. So, quadratic structure. A quadratic polynomial is a polynomial of degree 2. The standard form of a quadratic is ax squared plus bx plus c, where a is not allowed to be 0. Other than that restriction, all values are okay, positive and negative. Conventionally, we usually choose integers rather than fractions. If a polynomial has the value of 0 at a particular point of x, then that value of x corresponds to a factor of that polynomial. So if it has a 0 at 1, we will be able to turn that into a factor of x minus 1. If it has a 0 at negative 5, we have a factor of x plus 5. 0 is at 1/2. One factor is 2x minus 1. This will be important. If a quadratic factors, then it factors into something of the form. Remember, our variables in math are case sensitive, so capital A is not the same as lowercase a. So if you have ax plus or minus b and cx plus or minus d, then the roots should be at a as plus or minus, should be b over a and plus or minus d over c. Right, quadratics with a equals 1. If a equals 1, then our quadratic just looks like x squared plus bx plus c. Instead of factoring as ax plus or minus b and cx plus or minus d, we would just have x plus or minus b and x plus or minus d, because a and c are both 1. In this case, the roots are at the negative b and negative d. The term roots is synonymous with x-intercepts and zeros. So we want to see the signs, like ace of base in a music reference that most of you won't get because it was 30 years ago. So the signs on the linear and constant terms tell us a great deal about how a quadratic factors. If our constant term is positive, then the b and d in these factors are either both positive or both negative. They have to have matching signs. So when the constant is positive, b and d have to have the same sign. And they'll be matching our linear term, that term in the middle. If our constant is negative, b and d will have different signs. The larger value of b and d will have the same sign as the linear term. We'll do some concrete examples to make this more clear. So when we multiply them, we're going to have an x squared term from x times x. We're going to end with the product of b and d, and in the middle we're going to have the sum of the two. So our constant term then is the product of b and d. Our linear term is the sum when their signs match, or the difference when their signs differ. So we're either going to be adding or subtracting. So if we have x minus 2 times x minus 3, well, when we multiply these out, x times x makes x squared. The negative 2 times negative 3 makes a positive 6. Then we'll have a negative 2x and a minus 3x, so we're subtracting the sum of 2 and 3 times x. That's our negative 5x. So if we were to start with x squared minus 5x plus 6, we could ask ourselves, right, the sign is positive, that means the signs are going to match. The middle sign is negative. That means that the signs are both going to be negative. So then we need numbers that multiply out to 6, but add up to 5. and that's 2 and 3. More examples. Let's factor x squared plus 7x plus 12 if possible. All right, our constant term is 12, and it's a positive 12. The fact that it's positive says the signs in our factors will match, either both positive or both negative. The linear coefficient, that 7x term, is a positive 7. So both of our signs will be positive. Now we need factors that multiply out to make 12 and add up to make 7. So factors of 12 include 1 and 12. Those add up to 13. 2 and 6 add up to 8. And 3 and 4 add up to 7. So we'll have x squared plus 7x plus 12 equals x plus 3 times x plus 4. Right. Again, our signs match because the 12 is positive. Our 7x is positive, so that's how we know both signs are positive. And 3 and 4 are the numbers that multiply out to 12 and add up to 7. Let's factor x squared minus 2x minus 15 if possible. Our constant term is negative 15. Because it's negative, our factors will have different signs. Our linear coefficient is negative 2. So the greater of these two factors is negative. Right? It's 2 more than the other factor. So what numbers multiply to make 15 and subtract to make 2? The factors of 15 are 1 and 15. Those multiply to make 15, but you subtract them, you get 14. The other pair of factors are 3 and 5. They multiply out to 5, and when you subtract 5 minus 3, you do get 2. Because our cross term is negative and 5 is larger, 5 gets the negative sign, 3 gets the positive. So x times x is x squared. Negative 5 times a positive 3 is a negative 15. Now negative 5x plus 3x is a negative 2x. Now let's factor x squared plus 6x minus 8 if possible. Again, we have a negative constant term. That tells us our signs are going to be different. The linear coefficient is a plus 6. One factor has to be 6 more than the other. We don't have any integers that fit this. It does not factor with integers. Now this is tempting because 6 is 2 plus 4, and 2 plus 4 multiply out to 8. But our 8 is negative. To get there, we have to have a positive 2 and a negative 4, or a negative 2 and a positive 4. Either way, that linear term would be positive or negative 2. Because of the signs, it does not work. If that 8 was positive, we could factor it. Because it's negative, there are no factors that meet these criteria. In fact, the two roots are not even rational numbers. They involve the square root of 17. We will learn how to arrive at those in Math 20. Exercises. Let's factor x squared plus 9x plus 20 if possible. Pause now and take whatever time you need. All right, unpausing to reveal the answer. Constant term is positive 20. Linear coefficient is positive 9. So we've got matching positive signs that multiply out to 20 and add up to 9. That is 4 and 5. Now, x plus 5, x plus 4 is just as correct as x plus 4 times x plus 5. Here, factor x squared plus 4x minus 21 if possible. Our constant term is negative 21. Again, our signs will be different. The linear coefficient is positive 4. The greater factor is positive. Factors have to multiply out to make 21 and subtract to make 4. Well, we do have factors like that, So it's x plus 7 times x minus 3. The 7 has to be positive to get us that plus 4x in the middle. If the signs are the other way around, it would be x squared minus 4x minus 21. Now, this exercise, we're going to factor out x squared minus 6x plus 55 if possible. Pause now, take the time you need. All right, our constant term is a positive 55. We would need two factors with the same sign. Our linear coefficient is negative 6. So the factors have to add up to 6. There are no integers that fit this criteria. Again, if we had a negative 55 with either a positive or negative 6x, we could do it with 11 and 5. But that 55 is not negative, it's positive. We can't subtract 11 and 5. We have to find numbers that add to 5 and multiply to our constant. This polynomial has no real roots. Whatever the numbers are, they don't fit on the number line. In summary, if x squared plus bx plus c factors at all, the factors will be x plus or minus a constant b. If the constant term, that lowercase c, is positive, b and d have the same signs. They have to multiply out to make the constant and add up to the linear coefficient. If that constant term c is negative, b and d have different signs. You've got to subtract them to make the linear term if the factoring is possible. Now, if you have any questions, if you have any feedback, please leave it in the comments. And I will try my best to get back to you with a response in a timely fashion.